Welcome to 31st lecture of course Polymer Science and Technology. In this lecture we will see the effect of processing variable on extruder output. So first of all let us examine the effect of screw RPM. So we know that the output of extruder is given by equation number 2 in the previous notes, an minus c delta p over mu. Okay, so from this equation the extruder of the output is directly proportional to RPM, capital N, and the die output or the flow rate of the die is given as K delta P over mu. Okay, so let us consider that this is my die characteristic curve DCC, and we are operating our extruder at two different screw RPM, N1 and N2. So the first screw characteristic curve is the curve at the rate of N1 RPM. When we increase the RPM, the output will increase and the screw characteristic curve will offset in the upper direction and we'll get the second curve like this. So my next operating point will shift from the point number 1 to point number 2, and we can see by increasing the RPM of the screw, my operating point is shifting from point 1 to point 2, and point 2 is output corresponding to point 2 is higher than the output corresponding to my previous operating point 1. At the same time, the pressure drop across the die delta P will also be higher as compared to previous pressure drop corresponding to point number 1. So by increasing the RPM, output will increase. So this is the moral of the story, that when we increase the RPM, output will increase. But this is not the complete story. Why? You can see the output of a die is inversely proportional to the viscosity of the resin. So if the viscosity of the resin is going to change, means if viscosity of resin is going to decrease, then what will happen? Output of the die will increase. And we know from the viscometric plot for a polymer, when we'll increase the shear rate, the viscosity of the resin will drop. Okay, you can refer back to unit 3 for the viscometric plot. So by increasing the RPM, the viscosity will drop, and by dropping of the viscosity, my output, die output, will increase. So what will happen? This die characteristic curve will also change its position, and depending upon the position, the output has to measure again. So for certain range of screw RPM, we can say that the output will also increase, but beyond a certain limit, if we'll keep on increasing the RPM of the screw, a point will come where output of the extruder will not increase, rather it will start decreasing. Second point is the processing temperature, TP. So as I have already explained that the viscosity is a function of the temperature, and viscosity decreases with the increase in the melt temperature. Therefore, at higher processing temperature, extruder output will also increase and die output will also increase according to equation number 2 and 6. When viscosity will decrease, extruder output will increase, and when viscosity will decrease, die output will also increase. So you can say we are operating our extruder at two different temperature T1 and T2. So at T1 this is my screw characteristic curve and this is my die characteristic curve, and point number 1 is my first operating point. But when we will increase the processing temperature to temperature T2, the next screw characteristic curve is this one, and the die characteristic curve at temperature T2 is this one, and point number 2 is the new operating point. So we can see that the output of the extruder will increase with the increase in the temperature. Therefore, if we will increase the temperature, melt temperature, then output will also increase. But it doesn't mean that we can increase the temperature endlessly, because at the higher temperature the polymer will start degrading. So there is a check. We cannot increase the temperature beyond a certain limit. We should not reach closer to the degradation temperature of the polymer. Next is the die opening or the diameter of the extrudate. When die orifice diameter reduces, the pressure drop delta P across the die will increase. Therefore, operating point will shift from point number 1 to new operating point number 2. Hence, the output Q will reduce from Q1 to Q2. So, we can see that by narrowing the orifice diameter, the output will decrease, whereas the pressure drop will increase. The second most important melt processing technique is the injection molding. In case of injection molding machine, we can divide this injection molding system or machine into two or basically three parts. First is the injection unit, second one is the clamping unit, and the third one is the control unit. Injection unit is very much similar to the construction of an extruder that we have already discussed in the previous classes. The difference between the screw barrel assembly of an extruder and an injection molding machine is that in case of extruder, screw is fixed. Screw rotates about its axis, but it will not move forward and backward. Okay, whereas in case of injection molding machine, the reciprocating screw is used. That means a screw will not only rotate about the axis of the rotation, its axis, but it will move backward as well as it will move forward during the injection of the molten plastic material inside the mold. Okay, so in case of injection molding machine, screw can rotate as well as it can move to and fro from hopper end to nozzle end. Okay. So the plastic raw material is being fed from the hopper. It goes to the feed zone similar to the extruder, and the solid polymers moves from the feed zone to transition zone, and from transition zone to metering zone. All the three zones of extruders are also present in case of an injection molding machine. Okay, so when polymer moves from the hopper to the metering zone, what is the difference here? In case of injection molding machine, it gets accumulated in front of screw tip, and when it gets accumulated in front of screw tips, it applies a pressure on the screw in the backward direction, and there is an arrangement with the help of a hydraulic cylinder, and this screw moves back while rotation. Okay, so it moves back, so material is being plasticized, it is coming and accumulating in front of the screw tip, while at the same time screw is rotating, as well as it is moving backward under the pressure of the melt in front of a screw tip, and this pressure is known as the back pressure. Correct. So when the desired amount of molten polymer is being accumulated in front of a screw tip, so here what do you mean by the desired amount? Desired amount means the amount required to fill the cavity of the mold as well as runner system completely. So when desired amount of the polymer is being accumulated in front of a screw tip, screw will stop its rotation and it will stay here. Okay, so during the injection stage, hydraulic cylinder which is attached to the reciprocating screw will push this screw in the forward direction. That's mean from hopper to nozzle direction, and when this screw will move in the forward direction, it will push or it will pressurize the molten polymer already accumulated in front of a screw tip to flow from the nozzle to the runner system and finally to the cavity of the mold. So this is known as the injection phase. Electrical band heaters and motor for the rotation is also same as in case of extruder. Now in clamping unit, this is means this unit is not in the extruder system, this is the part of injection molding system. So in clamping unit, there are basically three platens. First platen from the nozzle side is the fixed platen. The second platen is the moving platen that can move to and fro for the opening and closing of the mold. And the third platen is tailstock platen, and it holds the hydraulic cylinder and the piston. This hydraulic cylinder and its piston connects the moving platen with tailstock platen. That's mean when the cylinder will expand, moving platen will move towards the right hand side and it will close the mold, and when hydraulic cylinder is oil flows in such a direction that hydraulic cylinder moves back, so it will open the mold. You can see this is the piston and it can move forward direction and backward direction, so it will assist in the opening and closing of the mold. Then you can see there are tie bars. This is a tie bar which is a very strong metallic bar connecting the tailstock platen to the fixed platen, and the moving platen can slide on the tailstock. Moving platen can slide onto the tie bars. So there are 4 tie bars. 2 tie bars are visible and 2 tie bars are just behind these 2. Okay, so there are 4 tie bars. You can see tie bars multiplied by 4, so that means there are 4 tie bars. Okay, and Each tie bar has tie bar nuts that holds the fixed platen and the tailstock platen connected to the tie bar. So the role of the tie bar is that it will assist the movement of the moving platen onto the tie bar, as well as during the clamping stage the strain energy is stored in the tie bar by slight increment in the length in the tie bar. You can say increment in the length is in the range of less than 1 millimeter, somewhere 0.7 0.8 millimeter. So this is very minute strain on the tie bar, but since tie bar is very strong, the modulus of elasticity of the tie bar is too much and the diameter of the tie bar is also enough, so it stores lot of strain energy, and that strain energy is used to keep the mold tightly closed under very high injection pressure of the melt, which is being exerted by the forward motion of the screw. So this is very much required. If proper clamping force is not being applied, then what will happen? Under such a high injection pressure of the melt, the mold will open from its parting line and polymer will come out from the parting line. So this is very important to keep the mold closed under very high clamping force, and this clamping force is initially provided by the hydraulic cylinder, and once the tie bars are extended for less than 1 millimeter strain energy is being stored, then hydraulic cylinder is cut or stopped, and the strain energy stored in the tie bar keeps the mold closed for the rest part of the molding cycle. Okay, so platens are clear, tie bars is clear. Now you can see the mold. The injection mold is mounted between the moving platen and fixed platen with the help of clamps. Okay, and the sprue of the mold is just in front of the nozzle, so that the molten polymer, which is being pushed by the forward action of the screw, can flow through the nozzle directly inside the sprue and finally to cavity of the injection mold. And injection mold is of basically two parts. One, the part which is attached to the fixed platen is known as the fixed mold half, and the part which is attached to the moving platen is known as the moving half of the mold. And usually the moving half of the mold contains the ejector system. This ejector plate holds ejector pins that connects to the mold cavity, and the ejector rod shown here, the ejector rod will move forward and it will push the ejector plate. So ejector plate along with all the ejector pins will move forward when mold is opened, and finally by the forward motion of the ejector pins, product will be ejected and it will fall out of the mold, and molding cycle will be repeated for the next shot. So this part is known as the ejection of the molded component. Okay, and this is the schematic of reciprocating screw type injection molding machine. Now let us see the explanation. The injection molding is a polymer processing technique widely used for manufacture of complex 3D parts like cabinet of a mobile phone, television, bumper and dashboard of an automotive, etc. injection molding is most widely used for thermoplastic polymers, but it can also be used for thermoset like phenolic resin, etc. There are four major types of injection molding machine known as plunger type, screw plunger type, plunger type, and reciprocating screw type. So the first three are the old design, and you can read the working and construction of plunger, screw plunger, and screw plunger type injection molding machine as a self-reading assignment. And we have already explained the reciprocating type injection molding machine, and now let us see the detailed explanation of reciprocating screw type injection molding machine. Let me tell you briefly, in plunger type injection molding machine there is a plunger, simple plunger that pushes the molten polymer, the polymer which is already molted in molten state by the help of electrical band heater heating inside the barrel. So the plunger will push it across a torpedo, and when it will flow out of the injection molding machine, it will go inside the mold and it will form the molded product. But this type of injection molding suffers from the homogeneity of mix because there is no shear mixing. So the quality of the polymer melt is not very good in case of plunger type injection molding machine. The second type injection molding machine is combination of an extruder and a plunger type injection molding machine. The purpose of screw extruder is just to plasticize the melt, and the melt goes inside the chamber of the plunger type injection molding machine, where plunger moves forward and backward to inject the polymer into the mold. So there are two parts, one screw that continuously plasticizes the polymer, and plunger pushes it, forces the polymer melt to flow inside the mold. Plunger type injection molding machine, first plunger is being used to plasticize the polymer, second plunger is used to inject the molten polymer inside the mold. In case of reciprocating type injection molding, the screw it rotate to plasticize, then it stops, and then it pushes the polymer just like a plunger. So it has dual role. First it will act as a screw, and second it will act as a plunger to inject the polymer. So as suggested by its name, plasticizing screw has two functions: plasticization of polymer, that is the melting, which is accomplished by the rotation of the screw, shear mixing and heating, so polymer will get plasticized or melted inside the screw barrel. The second is injection of plasticized polymer into the mold, which is an operation similar to the plunger type injection molding machine. Reciprocating screw type injection molding machine has three fundamentals unit: injection unit, clamping unit, and control unit. I have already explained you. Now let us see the injection unit in detail. Screw is rotated with the help of a hydraulic motor, and screw plasticizes the polymer by applying shear stress onto it. Molten polymer gets accumulated in front of screw tip. A non-retain valve (NRV) prevents the backward flow of the molten polymer. As we have studied that in case of extruder, the drag flow and the back flow. So in case of injection molding machine, to avoid the backflow of the polymer, non-retain valve is being used. So this non-retain valve will allow the flow of the polymer from hopper to the nozzle direction, but it will not allow the flow from nozzle to hopper direction. Okay, that's why it is known as the non-written wall. And it is very important to have NRV, otherwise during the injection phase a portion of polymer will flow in the backward direction. So NRV prevents the backward flow of the polymer during the injection stage. Molten polymer applies pressure on a screw. When it gets accumulated in front of a screw, it applies a pressure on the tip of the screw. Under the material pressure, screw moves backward linearly towards hopper. This pressure is known as the back pressure. So back pressure is the pressure exerted by molten polymer onto the tip of the screw. After plasticizing the required quantity of molten polymer, slightly more than the short size of the mold. Short size of the mold means the volumetric capacity of the cavity along with the runner and sprue system. So we have to plasticize the melt slightly more than the short size of the mold. Screw tips its rotation and sometime it moves backward for few millimeters to avoid drooling of molten polymer from the nozzle. This action of the screw is known as suck back. Suck back is usually applied in case of flow of low melt viscosity resin like nylon 6, etc. So if we'll not apply the suck back in case of low viscosity resin, what will happen? The material which is accumulated in front of a screw tip, it will start coming out from the nozzle itself, and this action is known as the drooling of the molten polymer. So we don't want the drooling of the polymer, we want to avoid the drooling of the polymer. So in order to avoid the drooling of the polymer, we will suck back. Suck back means the screw will move few mm, 5 mm, 6 mm or 10 mm, it will move backward so that the melt pressure is reduced and molten polymer should not flow out of the nozzle before injection. Finally, the screw is pushed forwards towards the nozzle by the hydraulic cylinder attached to the hydromotor. Hydromotor is the motor required for the rotation of the screw, and hydraulic cylinder is required for the forward or injection stage of the screw. Okay. Under very high pressure, approximately 150 to 180 bar. So this is the pressure at which hydraulic cylinder will operate. This pressure is further intensified due to differential area of the screw and cylinder, because the area of the hydraulic cylinder is much larger, at least 10 times larger than the area of the cross-sectional area of the screw. So the pressure of 150 bar will be intensified 10 times. It will become something like 1500 bar or 1800 bar injection pressure that will exert on the molten polymer. Therefore, injection pressure applied on polymer is in the range of 1200 to 1400 bar. So this is a very huge pressure under which molten polymer will flow from the injection unit to injection mold through the nozzle. Under such a high injection pressure, molten polymer flows through the nozzle into the cavity of the mold via sprue and runner system. Now let us see what is the sprue and runner system. For example, this is my cavity. This is a cavity of a you can say this is a molded glass of water. Okay, and injection point is just at the center of the bottom, and this is my injection point. So this is the sprue type runner. So nozzle will be connected here and molten polymer, first of all it will flow through the sprue runner and then it will be distributed inside the cavity. So this is the case of the single cavity. We may have more than one cavity in single injection mold. For example, there is a two cavity. This is one cavity, this is another cavity. Let us assume that two balls are there, one and two cavities. So this is my sprue. Injection unit will connect here. Molten polymer will first of all flow through the sprue, then it will flow through the runner. This is my runner, one runner, this is a second runner, and from runner it will flow through a very restrictive space which is known as the gate. It will flow through the gate and then finally it will enter inside the cavity. Why the cross-sectional area of the gate is very small? Because we want that the gate should freeze just immediately after the injection, so that there is no chance of backward flow of molten polymer from the cavity to the runner system and back to the injection unit. So what will happen, because of very narrow cross-sectional area, the gate will freeze immediately after injection, and once the gate is frozen, solidified, it will not allow the backward movement of the molten polymer from cavity to injection unit. This is another example of 8 cavity balance runner system. The injection point is at the center, then it is divided into 2 branches, and finally these 2 branches are subdivided into 4 branches, and 4 branches are finally subdivided into 8 branches. So this is the primary runner, secondary runner and tertiary runner, and tertiary runner is attached to the cavity with the help of gate for each and every cavity. So this is the balance runner system. Balance runner system means that the distance from the injection point to the cavity is same. You can see the same distance polymer has to travel to reach each cavity. It's not like that this cavity or this cavity will be filled first and the cavity which are away from the injection point will be filled at the last. This is the balance runner type design, that each and every cavity will be filled at the same time. Okay, so such a design is known as the balance runner system. When cavity is completely filled with the polymer under injection pressure, material has tendency to flow back into the barrel of injection molding machine. The backflow can be prevented by applying lesser pressure for extended duration of the time till the gate is completely frozen. This pressure is known as holding pressure, and the extended duration of time is known as holding time. Okay, so this holding pressure is also being applied by the tip of the screw. Injection pressure is also being applied by the forward motion of the screw, and holding pressure is also being applied by the reciprocating screw. Okay, so let us see that this is my injection mold and this is the cavity, and polymer is being injected through the sprue system inside the cavity, so polymer will flow. These are the flow fronts, and finally the entire cavity will be filled with the polymer. So when entire cavity is filled with the polymer, then you have to wait till gate is completely frozen, and for this we have to apply the holding pressure for the duration of holding time, so that gate is completely frozen. Let us say that we have applied a cavity pressure transducer or sensor that can measure the pressure inside the cavity, and it sends the signal of cavity pressure data with respect to time. So here we can plot my cavity pressure versus time. Okay, so initially from position A to B, you can see that for this much period of time there is hardly any increase in the pressure, because at this particular stage the polymer melt has not reached to the tip of my sensor. It is still flowing near the injection point. It hasn't touched the tip of the sensor. And at point B, the molten polymer reaches and start pressurizing the pressure sensor, tip of the pressure sensor. So the pressure will be realized at this point B, and as soon as more and more polymer is coming and pressure is increasing inside the cavity, you can see this is my filling phase, where pressure of the cavity is increasing up to C. From B to C is my filling phase, and at the point C, the time taken to reach from A to C is known as T fill, or time taken for the filling of the cavity. This is known as T fill. So at the point of C, the cavity is completely filled. Okay, but still you have to pressurize the melt in order to avoid the voids and shrinkage of the molded component. So you need more and more pressure to compress the melt inside the cavity. So from C to D is the packing phase. In packing phase you will apply more injection pressure, huge injection pressure. So you can see the point T is at the peak packing pressure, and at point D my cavity is highly compressed state. After point D, I have to wait till the gate is completely frozen, but I need not to continue at the pressure at the point D. We can apply a lesser pressure, which is the holding pressure, and somewhere about at point E. So we'll apply the holding pressure at E, and this will continue till point F. So this duration of time is known as T hold, or holding time. And from C to D, this time duration is the packing time. So you can see the packing time is very less. Usually it is a fraction of a second. Okay, whereas the T hold is the much larger. You need to wait till gate is completely frozen. So the gate is going to freeze, or gate is going to seal at point F. So holding time will end at point F. Now pressure will further decrease in the cavity. Why it will decrease? Because upon cooling the material will undergo shrinkage, and when material will shrink the pressure will decrease, and this is the residual cavity pressure with respect to time, and at point G the mold will open and molded component will be ejected. So this time duration from F to G is the additional cooling time, you can say. So this is the additional cooling time, or you can say cooling time, because cooling will start actually from, you can say, just after the point C. So cooling is from point C to G, but this time is being considered as a part of injection phase. Typically cooling time is considered from F to G. Okay, that's why we have called this additional cooling time. Okay, so this is the end of lecture 31st, and we'll continue with the injection molding in the next classes. So thank you very much.